Welcome to the Deep Dive. Today we're plunging into a really fascinating development in AI. It's all about how large language models, LLMs, are getting smarter faster. And, maybe most importantly, without needing constant human guidance. We're looking at a major step forward in LLM optimization, one that tackles some pretty core challenges. Our focus is a paper called DuPO, Enabling Reliable LLM Self-Verification via Dual Preference Optimization. It's by Shuaiji Shi and colleagues, and its core promise is, well, pretty compelling. Reliable, annotation-free feedback for these models. So our mission today is to unpack how DuPO rethinks self-supervision. We want to understand what this generalized duality concept really means, and explore the kind of results it's getting on tough tasks, like translation and math reasoning. This deep dive is for you. Maybe you're prepping for a meeting, catching up on AI, or just curious about how these models evolve so quickly. Okay, so LLMs have made incredible strides, haven't they? Tackling complex problems, areas like math reasoning, multilingual translation, stuff that seemed purely human not long ago. But the big question is always, how do we make them even better?
More capable, especially when we hit limits with existing data or human input. Historically, the main ways to boost LLMs relied heavily on, well, outside help. One key method is reinforcement learning from human feedback, RLHF.
Right, RLHF. It's great for aligning models with, human preferences, what feels right or useful, but it's expensive, takes a lot of time. And getting consistent human feedback, especially for really complex or nuanced tasks, that can be tricky.
And the other main approach, that's RLVR, right?
Yes, reinforcement learning with verifiable rewards. That works well for tasks where there's a clear right or wrong answer. Think math problems or maybe code generation. You get a definite binary reward, correct or incorrect. It cuts down the human annotation need, but it still needs that external check, some ground truth. And it struggles with open-ended things like translation, where there isn't just one single correct output.
So the common thread there for both RLHF and RLVR is this dependence on external supervision. Someone or something outside the model has to validate it.
That's the core limitation. It really creates a bottleneck. It limits how scalable these approaches are and how adaptable they can be across the huge range of tasks we actually want LLMs to handle without us holding their hand the whole time.
So before DuPO, there was this idea of dual learning trying to tackle this, aiming for self-supervision. Using task duality, right?
Yeah.
Like translating something and then translating it back to check.
The classic example is translation and back translation. Translate English to French, then that French back to English. In theory, the model could check if the final English matches the original. Cycle consistency.
Sounds like a neat self-correction loop. Why wasn't that the perfect solution for LLMs then?
Well, it ran into a couple of fundamental problems when applied to the kinds of complex things LLMs do. First, there's what the paper calls limited duality and irreversible tasks. Most real-world LLM tasks just aren't strictly reversible in a way that gives you enough information back. Take mathematical reasoning. If the LLM figures out, say, 3 apples plus 5 apples is 8 apples and just outputs 8, that number 8 alone doesn't contain nearly enough data to reconstruct the original question, was it apples? Or something else adding to 8. This lack of reversibility breaks that neat cycle consistency check. The self-supervision signal gets lost.
Okay, so the information just isn't there in the output. What was the second challenge?
The second one is bidirectional competence asymmetry. Basically, LLMs are often much better at the main task, the primal task, than the reverse task, the dual task. An LLM might be great at solving a math problem, but pretty poor at generating a unique, sensible word problem from just the answer 8. So if the dual task performance is weak or noisy, the self-correction signal it generates is also weak or noisy. And that hinders the whole optimization process. These issues made traditional dual learning not quite right for general LLM improvement.
Okay, let's unpack this. So DuPO comes in with this idea of generalized duality. That sounds like the key innovation here. How does it get around those problems, the irreversibility and the competence asymmetry? Is it a fundamentally different way of setting up the self-check?
It is. DuPO's core idea is to redefine task duality. It moves away from needing a strict, perfect input-output reversal. Instead of trying to reverse the entire process, which, as we said, is often impossible, DuPO cleverly decomposes the input. It splits the input into 2 parts. A part the model already knows, the known component, and a part it needs to figure out or use, the unknown component.
Okay, so you break the input down first.
Right. And then the dual task is designed very specifically. Its only job is to reconstruct just that unknown component. And it does this using the output from the main task and that known component you kept aside.
Ah, I see. So you're not asking it to reverse everything, just find one missing piece using the answer and another piece of the original input.
That's the essence of it. This framework restores enough information flow for the self-check to work, and it drastically reduces the difficulty of the dual task, making the signal more reliable.
Can we walk through a simple example that might help make it more concrete?
Sure. The paper uses a simple two-sum example, like calculating A plus B. So the primal task, TP, is straightforward. Compute A plus B equals C. C is the output Y. Now, for DuPO, we decompose the input. Let's say A is the known component, xk, and B is the unknown component we want the dual task to find. The complementary dual task, TCD, then aims to reconstruct B. It takes the output cy and the known part A, xk, and performs the operation ca. This gives a reconstructed value, let's call it B. The self-supervised reward then just checks. Is B consistent with the original B? Does B equal B?
Okay, that makes sense. By providing A, you give the dual task enough context to isolate B from C. So how does this generalized duality directly tackle those big challenges we talked about earlier, the irreversibility and the asymmetry?
It addresses them quite elegantly. The paper highlights three main advantages. Remark 1, they call it. First, it overcomes the invertibility constraint. Because you're only reconstructing a selected unknown part, you don't need the primal output Y to hold enough info to get back the entire original input. This immediately opens up dual learning to tasks that are inherently non-invertible, which is most complex tasks.
Right, you sidestep the need for perfect reversal. What about the competence asymmetry?
Second, it mitigates competence asymmetry. That known component, xk, like A in our example, acts as a strong anchor. It really narrows down the possibilities for the dual task. Reconstructing just B from C and A is much easier than trying to guess both A and B from C alone. This makes the dual task easier, leading to a more reliable, less noisy reward signal. It avoids that weak dual problem.
And the third advantage?
It enables broad applicability by solving those first two problems. DuPO essentially unlocks dual learning for a whole range of important LLM tasks that were previously off limits to this kind of self-supervision. We're talking mathematical reasoning, code generation, even dialogue systems, where the input-output relationship isn't a simple symmetric one.
So DuPO uses this generalized duality framework for what it calls preference optimization. It seems like it's basically teaching the model to prefer outputs that are internally consistent, according to this clever dual task check. And the big claim is that this happens entirely without needing external human annotations. That does sound like a potential game changer.
That's the core mechanism. It leverages the complementary dual task to generate its own reward signal. This reward reflects the internal consistency or correctness of the primal output as judged by the dual task. The model then optimizes its behavior to maximize this expected self-generated reward. This effectively removes the dependency on costly and sometimes inconsistent human feedback, making the process more scalable and autonomous.
Okay, the theory sounds solid, very clever, but how does it perform in practice? What kind of real-world results is DuPO actually delivering?
The empirical validation is quite strong. They tested DuPO on two very different demanding tasks: multilingual translation and mathematical reasoning.
Let's start with translation. How did it do there?
For multilingual translation, they applied DuPO to seed X7B instruct. This is already a pretty capable open-source translation model, a 7 billion parameter one. DuPO delivered a significant gain, 2.13 COMET points on average. And this was across a massive test set 756 translation directions covering 28 languages.
COMET points, that's a standard metric for translation quality, right? Is 2.13 points a big deal?
It's a very meaningful improvement in translation quality, yes. COMET is well regarded because it correlates well with human judgment. This boost actually pushed the 7B model's performance into the same league as some ultra-large, state-of-the-art systems like GPT-4o and DeepSeek-R1. And importantly, in human evaluations, it significantly outperformed widely used commercial systems like Google Translate.
Wow, okay. So closing the gap with much larger models and even beating commercial giants in human evils, that's impressive for translation. But translation has some flexibility.
Yeah.
What about mathematical reasoning? That demands precision. How does DuPO handle that?
Mathematical reasoning was the second major test case, and the results were equally compelling. DuPO showed robust gains across models of different sizes, from 1.5 billion parameters up to 7 billion. For example, on the Qwen 3 4B model, DuPO improved accuracy by an average of 6.4 percentage points. This was on 3 really tough math benchmarks: AMC23, AME24, and AME25. These are competition-level problems.
6.4 points on those kinds of tests is substantial.
It is. It actually allowed that 4 billion parameter Quen model to outperform the much larger DeepSeek R10110 on those benchmarks. They also tested it on a very strong reasoning model, Open Reasoning Nemotron 7B. DuPO pushed its average score up from about 84% to over 90%. Even on a smaller distilled model, the DeepSeek R1 distilled Quen 1.5B, which has less initial reasoning power, DuPO still delivered a solid 3.9-point increase.
So it's not just marginal gains. It's enabling smaller models to perform like much larger ones in some cases. And it seems like this approach isn't tied to one specific type of LLM architecture. You mentioned Quen, Nemotron. Does it generalize?
Yes, they specifically tested for that. DuPO showed scalability across different backbones. They ran experiments on models from the Llama family, Llama 3.18b, and OctoThinker 8b hybrid base. Both demonstrated broad effectiveness. Llama 3.18b saw a huge plus 24.0 percentage point gain in average score, outperforming other RL methods significantly. OctoThinker 8b, which had already had some middle training, showed even bigger jumps on specific tests, plus 50 points on AMC23, plus 27.4 on MAT 500. Its average performance hit 62.5%. So yes, it seems quite robust across different architectural foundations.
That's really interesting. So it's not just fine-tuning existing skills. You mentioned earlier it might even help models learn reasoning.
That's one of the most intriguing findings. DuPO seems to incentivize reasoning capability directly from a base model, even without specific supervised fine-tuning for reasoning first. Looking at the training process, the forward accuracy, basically, how well the model did on the main task during training is shot up from around 15% to nearly 57%. And this learned skill wasn't just memorization, it generalized well. Performance on unseen test sets like AMC23 jumped dramatically from 20% baseline accuracy up to 70% after DuPO training. Similar leaps were seen on AME24 and AME25.
So it's actually learning the process of reasoning through this self-consistency check. And there was something about using it during inference time, too, without any extra training.
That's right. DuPO can also function as a training-free inference-time re-ranking strategy. The idea is you generate multiple possible answers or reasoning paths from the model. Then you use DuPO's dual task mechanism to assign a self-supervised reward, basically a confidence score, to each path based on its internal consistency. Finally, you select the answer or path with the highest DuPO reward.
Like the model judging its own work to pick the best attempt.
Essentially, yes. And this re-ranking alone provided significant boosts. On math reasoning, just using DuPO re-ranking improved the Quen 3.4b model's average performance by 9.3 percentage points. That pushed it from about 68% to nearly 78% accuracy, allowing it to outperform DeepSeek R1 and even Claude Sonnet 4 thinking just by selecting better among its own generated answers. And for the smaller 1.5b parameter model, the effect was even more pronounced, an 18.7-point increase from re-ranking alone.
Wow. That's a huge gain without any retraining. Did they look into why it works so well? What's the key part of the DuPO making this happen?
They did some ablation studies. These confirm that the specific strategy DuPO uses for selecting that unknown component in the dual task is really crucial. Getting that decomposition right is key to reducing noise during training and ensuring you have a high-quality, reliable duality relationship for the self-check.
Okay, bringing this all together then. For someone tracking AI developments, what are the key takeaways from DuPO?
Well, DuPO really stands out as a significant step forward in LLM optimization. It's a dual learning-based preference optimization framework. That's the technical description. But what it does is tackle fundamental limitations, the high cost of human annotation, and the problem that most tasks aren't perfectly reversible for traditional dual learning. Its main advantages are clear. It's annotation-free, which means it's cheaper and faster to scale. It's versatile, working across different tasks like translation and math and different model architectures. And it's effective both for improving models during training and for boosting performance at inference time without retraining. It really opens up a path for LLMs to become more autonomous, aligning themselves with complex goals using their own internal feedback mechanisms.
It makes them more cost-effective and potentially more capable learners on their own, which does lead to a fascinating final thought. As these AI models get better at self-correction, at learning from their own outputs without constant human guidance, how might this shift our very definition of learning or even intelligence in these artificial systems? What new doors does this kind of autonomous improvement open up? Something to ponder. Thank you for joining us on this deep dive into DuPO. We hope you'll continue exploring this rapidly evolving field